nuclear weapons are necessary to the defense of the United States, to the deterrence of an enemy attack that could be launched at any time against any target in the free world. The military role of the United States therefore involves the daily shipment of atomic weapons over the road, by rail, in ships at sea, and in aircraft. These atomic weapons may only be passing through, or they may be stored near your town at a military base, or an emplacement site for air defense weapons. Exactly what hazard is involved in this movement of atomic weapons throughout America? What problems might it present to the firemen in your community? False and misleading stories in scare magazines and other publications may have created a certain amount of fear. The fear of a local atomic blast, the fear of exposure to radiation. The purpose of this film is not to teach firefighting, but merely to dispel that fear, replacing fiction with the facts. These are incorporated in Defense Atomic Support Agency Technical Letter 20-6 and the AEC DoD Technical Information Bulletin dated 30 September 58 on the same subject. What do atomic weapons look like? There's nothing exotic or mysterious about their appearance. They look like what they are, bombs or rockets. Thousands of Americans work every day with radioactive materials and atomic weapons. If you know what you're doing, if you observed a few simple precautions, this kind of work is not as dangerous as driving the family car. The trouble is, those words, atomic explosion, remind us again of the familiar fireball with its mushroom cloud and lethal radiation. But because of the special emphasis placed on the design, the manufacture, and handling of atomic weapons, the possibility of this kind of an explosion resulting from accidental detonation while they are in storage or during shipment is so remote as to be considered negligible. If the high explosive of an atomic weapon should accidentally explode near your community, the resulting blast and fire would look more like this. Property damage, injury, and loss of life would be relatively light and might not occur at all. With a few simple precautions, most of the hazards presented by scattering of the active material of the unexploded nuclear trigger can be eliminated or controlled. An atomic weapon is burning in this aircraft as these firemen move in to put out the fire. What do you have to know to deal effectively with this kind of a fire in this kind of accident? To begin with, there must be some understanding of basic principles involved. The principle of nuclear reaction is simple. When the nucleus of an atom of an active material, such as U-235 or plutonium, is struck by a neutral particle called a neutron, the atom splits or fissions into two or more parts. The combined weight, or more correctly, the mass of these fission fragments, is less than that of the original atom, and the lost weight or mass has been converted and released as energy, nuclear energy. During and as a part of the fissioning process, another reaction has also occurred. The atom has released 2 or 3 additional neutrons, which by striking the nuclei of other atoms can go on to continue the fissioning process. Essentially, it is a continuation of this reaction that makes an atomic bomb reaction possible. Because stray neutrons are always present, there are limits to the amount of active material that can be assembled without producing a premature nuclear reaction. If the amount or shape of the active material is such as to permit the neutrons given out by spontaneous fission to escape after only a few fissions, the nuclear reaction is not self-sustaining, and the condition of the mass is said to be subcritical. If the configuration of the amount of active material is such that one neutron from each fission does not escape and goes on to fission a new atom, a continuous self-sustaining action known as chain reaction is created, and the mass is said to be just critical. Let us see just how this active material, the nuclear trigger in our atomic weapons, is made to go critical. The nuclear component, or trigger, may be separated from, or it may be contained with the high explosive, or as it is commonly called, HE in the weapon, as it is here. The important thing about this fissionable material that serves as our nuclear trigger is that it must be compressed to reduce its volume. In explaining how we use HE to do this, we must first explain what is meant by implosion. In contrast to the bursting outward of an explosion, implosion is a bursting inward. To detonate an atomic weapon, both are employed. Explosion of the HE surrounding the nuclear trigger is accomplished by the simultaneous firing of many detonators around the surface of the charge. The wave from each of the detonators propagates inward. This imploding wave acts to compress or to squeeze the volume of fissionable material, which therefore fissions, releasing a burst of nuclear energy. The implosion system is based on the principle of increasing the criticality of the active material by squeezing the atoms closer together. The point to remember is that to produce an atomic explosion, there must be simultaneous detonation of the explosive charge around the nuclear trigger. This is accomplished by surrounding the HE charge with detonators. These are connected through a series of firing contacts to the electrically powered fusing and firing system. Voltage reaches all detonators simultaneously, and because it has no place to go, the active material is compressed by implosion. The active material goes critical, thereby causing an atomic explosion. Implosion of the HE charge against the nuclear trigger releasing this destructive force cannot, however, be accidentally caused. Detonated at any single point on its surrounding skin, and this is what would happen to any atomic weapon involved in a railroad, truck, or aircraft accident, there would be no release of nuclear energy because there would have been no implosion and no squeeze to make the nuclear go supercritical. The exploding wave moving from the single point of impact on one side to escape on the other would simply release and scatter the active material in the nuclear trigger. It would not release its tremendous nuclear energy. Let us consider, for example, the repeated tests conducted by the Department of Defense in which a variety of atomic weapons have been dropped from various altitudes to determine what kind and what magnitude of explosion or fire and damage might result from such an accident. In the low-altitude release of an atomic weapon, there was no fire, no detonation of the explosive material, which simply broke up and was scattered about the ground. No nuclear reaction was possible. In other tests, the ignition of propellants, fuels, or high explosives presented a more conventional problem than that of radioactive contamination or anything else relating to the atomic nature of the weapon so destroyed. Scattered and burning gasoline may be the only serious immediate aftermath of an atomic weapons accident. Or the burning of highly volatile and widely scattered propellants may result, starting secondary fires. In some cases, the HE in the weapon may explode. In any accident involving atomic weapons, high explosives will normally be your first concern. All HE is designed to detonate, and under certain conditions, it will. Rocket motors, when exposed to flames, will probably begin to burn within a minute and a half. Completely enveloped in flame, present atomic weapons may ignite in a few minutes. But in most tests conducted to date, the high explosive has not exploded. It has simply burned. No one can predict the exact reaction of a high explosive involved in any accident. Too many variables may be present in the situation or in conditions surrounding the weapons. But many tests have indicated that when involved in a large-scale fuel or propellant fire, the HE used in atomic weapons will probably burn rather than detonate. There are exceptions. High explosive detonations are primarily caused by a mechanical blow or shock transmitted either by a detonator, as we have seen, or some accidental means. The sudden force exerted on an HE system by violent impact may set it off. Such an accidental one-point detonation can cause a violent explosion. Heat generated by a surrounding fire, or the intense and protracted heat of a large fuel fire, might also produce a one-point detonation causing HE to explode. There are three conditions under which HE will detonate in fire. First, the type of HE involved is a factor. All high explosives used in our atomic weapons will burn. Second, HE will detonate if the quantity involved exceeds certain fixed amounts. The HE contained in our atomic weapons is well below these critical limits. Third, the degree of confinement surrounding the HE is a factor in determining whether it will detonate or not. Like water in a boiler without a pop-off safety valve, HE may be harmless in confinement until heat is applied. Then, just as water will boil, the HE's gases will expand in heat. And just as a boiler blows, the HE detonates, exploding out of its confining skin. But under the conditions with which we are here concerned, most military explosives, like this irregularly shaped 100-pound charge, will burn without detonation. There are certain characteristics of a burning high explosive with which you must therefore be familiar. Melting and flowing like this, it will spread, drip, and mix with debris. A dry extinguishing agent is not too effective against this fire. Neither is CO2, although it seems to be quenching this fire. Burning HE, which appears to have been extinguished by CO2, usually reignites. Water is an effective agent against burning HE. Cooling the molten high explosive below its ignition temperature with water will put out the fire. Foam applied to burning HE will also effectively control a fire. But foam adds to the cleanup job. Covering the fire as it does, foam conceals the extinguished but still dangerous residue. HE that has not completely burned remains as an explosive hazard. After it has been cooled below ignition temperature, it will, like metal, take on curious shapes. And while molten or burning, it may have picked up impurities, making it actually more dangerous than it was before melting. Never use a fire axe on this. This residue can still explode. So too can pieces of HE found out of reach of flames, but within sufficient range of heat to melt. This residue also poses an explosive hazard to unqualified handlers. In summarizing the explosives hazard present in a fire involving atomic weapons, remember this. There is almost no possibility that any part of the nuclear trigger will explode as a result of an accidental detonation of the high explosives in an atomic weapon. Tests indicate that with 2 or 3 not very likely exceptions, the HE systems in nuclear weapons will burn rather than detonate, although with burning explosives, detonation is always possible. High-order explosive detonations are more destructive than low-order explosives. A high-order detonation leaves no explosive hazard after the accident, but the surrounding area might be contaminated with scattered nuclear material. After a low-order explosion, melted, broken, unburned, undetonated explosives and scattered nuclear materials remain as a danger to the unsuspecting. And remember that burning HE can often be detected by its brilliant flame and usually white smoke, as compared to the red flame and black smoke of fuel fires. Unburned, undetonated residue may look like rock or compacted dirt. It can still explode. Only the white residue is inert and harmless. If the fire is small or controlled, and if the high explosive system does not ignite or detonate, we can be fairly certain the nuclear weapon is only superficially damaged. It is still a nuclear weapon. It should be left alone. Only qualified government emergency teams should be permitted to examine and recover the weapon. All others should withdraw to at least 1,500 feet. If the high explosive system has detonated or burned, some nuclear material, such as plutonium, which is an internal radiation hazard, may be scattered over the immediate area, even though there's been no nuclear explosion and no danger of fallout over a large area. This plutonium emits alpha radiation and can cause considerable damage to the body if it is inhaled, swallowed, or enters the body through breaks in the skin. Movement of personnel and vehicles should therefore be controlled and kept upwind of the immediate area of the accident. No one should enter this area except essential personnel. All others should be kept out of the smoke and at least 1,500 feet away. Anyone working in this area should wear a self-contained breathing apparatus and standard firefighting equipment. Radiation does not cover a surface like a coat of paint. Removing scattered hot spots may be the only decontamination required, but radiation cannot be seen. Only qualified monitors equipped with the proper meters can detect this contamination and establish safety boundaries at the scene of the accident. In an atomic weapons accident, we consider only the plutonium alpha contamination that may be dangerous if inhaled or taken into the digestive tract or into the bloodstream. A piece of paper will deflect or stop this alpha particle. The alpha particles have a very short range and lack the ability to penetrate the skin. This means they present no external hazard. Pending the arrival of capable monitors with the proper meters, all traffic to and from the scene should be controlled. Unauthorized persons and anyone not required on the scene should be kept at a distance of at least 1,500 feet. Now let us visit the scene of a hypothetical accident involving an atomic weapon. And let us see how trained personnel can cope with the problems we have discussed, safely completing their duties in a situation in which burning high explosives and even plutonium contamination may be present. Such an accident could happen. This one happened on takeoff from a military base. The plane crashed in rough ground beyond the end of the runway, a considerable distance from the strip. The aircraft is on fire. So is the atomic weapon, broken in the crash, the flame and smoke of its burning high explosive distinctly clear and white against the darker flames and blacker smoke of burning fuel. Negotiating rough terrain, crash trucks arrive. The senior officer of the fire department drops off to establish a control point. Fires of this nature should be fought only when lives or property are jeopardized. Only the senior officer can make the decision. For the purpose of pictorial presentation, the decision has been made to fight the fire. Approaching the burning plane from angles approximately 45 degrees to any gun or rocket armament mounted on the wings or nose, which in the heat of the fire might go off, the two crash trucks now move in, attacking the fire with all turrets applying foam. The firemen wear complete protective equipment. Checking the cockpit of the plane, one fireman is meanwhile determined that the pilot has escaped. The nearest military base or hospital having been promptly notified, an ambulance and doctor arrive. The pilot is placed on a stretcher and carefully covered, not only to protect him against shock, but also to prevent the spread of contamination from his clothing. He is then quickly dispatched to the hospital. Fully trained and working as prescribed, the firemen now move in with hand lines, closing in on the burning weapon itself. The commander of the military base from which the plane took off has also been notified of the accident. He or his representative arrives and joins the fire department officer. Military police will also promptly report to the scene. These men or any police officers will block all entry into the area, preventing the curious onlookers disasters always draw from entering the danger zone and preventing any compromise of security. Any newsmen, reporters, or photographers arriving at the scene are tactfully restrained from approaching the danger zone. Supporting equipment and men from other fire departments may also arrive on the scene. They may help in any way they can. Here, they join the crash crews in attacking the fire, which is soon contained. But when the fire is dead out, the hazards of unburned high explosives and of plutonium contamination may still remain. Without proper detection instruments, we just don't know. To be on the safe side, those firemen who have been working near the weapon and who may have been contaminated abandon their hose, which may have been contaminated too. Hand lines, which also may have been exposed, are disconnected and left at the scene to be monitored. Taken to the control point, they strip off all outer clothing which may have been exposed. Trucks are moved away from the wreckage, but only as far as the control point, where they are halted to prevent the spread of contamination. A monitoring team, meanwhile, has arrived. They may be called a nuclear emergency team, a disaster control crew, or an explosive ordnance disposal team. The important thing to remember is they know their job. Firemen of the supporting department wash down with a low-pressure stream of water the foam-covered remains of the atomic weapon, so that it can be examined by ordnance technicians of the monitoring team. The area is then immediately examined, and any classified material is destroyed or removed. Firemen who have been exposed to contamination are meanwhile taken from the control point to a decontamination station, which is always located upwind from the accident scene. Here, the men themselves are monitored for any contamination they may have on their skin or clothing. Should any be found, the man scrubs down immediately with soap and water. Contaminated clothing or protective equipment is sealed in a plastic bag for washing down or any decontamination process that may be necessary. This will later be returned to the men. Fire trucks and equipment used near any possible source of contamination must also be checked for radiation. And like the men's equipment, these vehicles will also be washed down and returned to service. Technicians have also established safety boundaries around the hot area containing any contamination. But since the ground is wet here and cannot be properly read by present meters, earth samples are taken. These will be dried out in the laboratory and monitored there. If the ground is dry, these samples will not be needed. The entire area is also carefully searched for scattered chunks of unburned explosive material. Still an explosive hazard, this will later be destroyed. And that's that. The fire is dead out. The remains of the weapon itself have been examined and any classified material removed. All suspected contamination hotspots have been found and cleaned up. And any unburned still explosive HE fragments have been collected and removed. Fighting this fire has been little more dangerous than any problem faced by firemen every day. You may have faced worse fire situations in the past. In summary then, if an atomic weapon is involved in a fire, there will be no nuclear explosion and no fallout. The greatest potential danger in an accident of this kind is the effects of blast caused by detonation of the conventional high explosives in the weapon. Also, detonation of the high explosives can result in contamination of a small area if nuclear materials are scattered. There is no danger of an atomic explosion, and the quantity of nuclear particles in each weapon is so small it does not constitute a major hazard. Decontamination is a simple washing procedure, and therefore evacuation of the type to cause public concern will not be necessary. Pertinent facts concerning atomic weapons in fires are contained in the official technical publications previously mentioned and may be obtained upon request through appropriate channels from the AEC for civil authorities and the DOD for military agencies. To stress a word of caution, cleaning up any residue should be accomplished only by qualified military or AEC emergency teams. Properly informed and equipped, firemen can cope with any fire resulting from an accident involving any of the atomic weapons now in the military inventory of the United States.